Now we have discussed about the subject C8395 strength of material for mechanical engineers. Unit 5 thick cylinder based on problems we have discussed. Unit 5 thick cylinder problems we have discussed. The course outcome of the in this unit after successful completion of the student should be able to apply the principal plane and stress in two-dimensional bodies and thick cylinders. The knowledge level of in this unit is K3. Problems. A cylinder pressure vessel has inner and outer radius of 200 mm and 250 mm respectively. The material of the cylinder has an allowable normal stress of 75 meganewton per meter square. Determine the maximum internal pressure that can be applied and draw a sketch of radial pressure and circumstantial stress distributions. So that is the problem. So once again I will read the problem. So you can read the problem one or two times. So that is also you can understand the given data. So once again I will read the problem. A cylinder pressure vessel has inner and outer radius of 200 mm and 250 mm respectively. So inner radius and outer radius are there. The material of the cylinder has an allowable normal stress of 75 meganewton per meter square. The normal stress is 75 meganewton per meter square. Determine the maximum internal pressure. So determine that is the fine value internal pressure that can be applied and draw a sketch of radial pressure and circumferential stress distribution and circumferential stress distribution also we have find out. So first of all you can write the given data. So already I told you, you can read the problem one or two times. What are the data you can understand, you can write the given data. So given data inside radius Ri is equal to 200 mm, outer radius Ro is equal to 250 mm. The allowable stress is equal to 75 meganewton per meter square. That is also converted to Newton per millimeter square, 75 Newton per millimeter square. Then outside pressure PO is equal to 0. That is assume value. We have assumed that the outside pressure P0 is equal to 0. Next we have apply the inside hoop stress sigma C is equal to 75 Newton per millimeter square. Then the radius, internal radius equal to 200 mm. Substitute in this equation for hoop stress. So we apply the hoop stress equations. 75 is equal to B divided by 200 square plus A. That is equation number 1. Once again, 75 is equal to B divided by 200 square plus A. That is equation number 1. Outside pressure P0 is equal to 0. Outside pressure B0 is equal to 0. That is we have assumed value. So 0 is equal to P divided by 250 square minus A. So 0 is equal to P divided by 250 square minus A. That is equation number 2. Now adding equation 1 and 2. So we have adding the equation 1 and 2. What will happen? 75 is equal to B divided by 200 square plus B divided by 250 square. So solving we get the B value, that is the B value 182926.8.29, that is the B value. So we have find out the B value. Next, substitute the value of B in equation 1 or 2. So we are using the 1 or 2. We apply the B value. We got the A value. A is equal to 29.268. A is equal to 29.268. That is the value of A. Next, determine the maximum internal pressure. Substitute the value of A and B. In this equation bar, pressure corresponding to radius Ri, that is inner radius. So first of all, we have calculate the pressure, internal pressure, maximum internal pressure, that is mentioned Pi. So Pi is equal to, we are using the formula P by 200 square minus A. So we are using the that formula will be, we are using, you know the value of P and A. We have applied the in this formula Pi is equal to 1829926.8.29 divided by 200 square minus 29.268. So we are simplifying the that values. We got the internal pressure 16.46 Newton per millimeter square. Or another one formulas are we are using P R is equal to circumferential stress minus 2A. Circumferential stress minus 2A. That formula will also you are using the solve the problem. So we have solved the equations. We got the internal pressure Pi is equal to 16.46 Newton per millimeter square. Next, stress on outer wall of the cylinder. So sigma minimum is equal to, we have applied the B value divided by 250 square plus, that is the outer radius, 250 is the outer radius plus A value 29.268. So we got the sigma minimum stress equal to 58.54 Newton per millimeter square. 58.54 Newton per millimeter square. That is the diagram, cross sectional diagram. The 200 is the inner radius, 250 is the outer radius, that is the origin point. So 16.46 megapascal pressure variation across the cylinder wall. Pressure variation across the cylinder wall. So that is 75 is the variation across the cylinder wall. Scoop stress variation across the cylinder wall. Okay, the maximum 75, minimum 58. So that is also variation pressure. That is 0. Outer pressure is 0. So inner pressure is 16.46 megapascal. That is the diagram we have drawn. So we have mentioned that is a hollow cylinder. That is a thickness of the cell. That is the thickness of the cell. The internal radius 200 mm, outer radius 250 mm. Then internal pressure is 16.46 megapascal. Outer pressure is 0. Then that is also hoop stress will be the minimum hoop stress is 58.54 megapascal. The maximum hoop stress is 75 megapascal. So another one formula also we are using the minimum stress calculated. The minimum stress equal to PR in plus 2A. So PR value is 0, 2A, 2 into 29.268. That is also same answer, 58.54 Newton per millimeter square. So you can using this alternative formula also find out the minimum stress. Next problem. A cylindrical pressure vessel has inner and outer radial 150 mm and 190 mm respectively. If the internal pressure in the cylinder is 50 megapascal, determine the maximum and minimum value of circumferential stress on the cylinder. Also find the circumferential and longitudinal strain on the inner and outer surface of the cylinder. So given Young's modulus also there, E is equal to 210 gigapascal, Poisson ratio mu is equal to 0.26. So once again I will read the problem. A cylindrical pressure vessel has inner and outer radii of 150 mm and 190 mm. So that is the inner radius, that is the outer radius. The internal pressure of the cylinder is given 50 megapascal. Determine the maximum and minimum value of circumferential stress. So we have find out the circumferential stress, maximum and minimum. Also find the circumferential and longitudinal strain. So we have find out the circumferential and longitudinal strains also we have find out. the inner and outer surface of the cylinder. Given the Young's modulus is given, Poisson ratio also given. So given data, you can write the given data. Inside radius R is equal to 150 mm, outer radius R was equal to 190 mm, inside pressure P is equal to 50 megapascal, outside pressure P0 is equal to 0. So next we know for the thick cylinder formula PR is equal to B by R square minus A. So inside pressure P is equal to 50 megapascal, corresponding radius of inner radius 150 mm. So we have applied in these equations. 50 is equal to P divided by 150 square minus A, equation number 1. Next, outside pressure P0 is equal to 0. That is, we are taking the assumed value. Outer pressure P is equal to 0. The corresponding radius, outer radius 190 mm. So you can apply this in this formula. 0 is equal to P divided by 190 square minus A. 190 square minus A. That is equation number 2. So subtracting equation 1 or 2 from equation 1. So 50 is equal to P divided by 150 square minus P divided by 190 square. So solving the B value, 2986213.24. Substituting the value of B in equation 2 or 1. So you can subtract the equation 2 or 1. So we got the A value. A is equal to 82.72. 82.72. That is the A value. So we go find out the B value and A value. Next we go apply the formula. Inside hoop stress sigma C is equal to P divided by R square plus A. P divided by R square plus A. Or another one formula, PR plus 2A. So we go apply the, taking the first formula we go using. So we go apply the B value, then R value is unknown, R square plus 82.72. So the R value is Ri. So we are using the inside pressure. So we are using the inside pressure. R is equal to 150 mm. So inside hoop stress, that is the maximum stress, sigma C. So circumferential maximum stress will be we have calculated. We have apply the B value, that is the R value, that is Ri 150 square plus A 82.72. So that is the maximum circumferential hoop stress. So maximum hoop stress 215.44 megapascal. Next, outer radius R was equal to 190 mm. So we are using this formula sigma C, that is the minimum hoop stress. We have applied the B value and R value. So R value is the outer radius will be applied plus A value 82.72. We got the answer 165.44 megapascal. That is the minimum hoop stress value. That is the minimum hoop stress value. Next we have find out the longitudinal stress in the cylinder. Longitudinal stress in the cylinder. So the formula sigma L is equal to Pi Ri square divided by Ro square minus Ri square. So we can apply the all the given values and calculated values. So we apply the Pi, that is 50 into Ri square 150 square divided by outer radius square minus inner radius square 190 square minus 150 square. So we are simplifying the that values. We got the answer of longitudinal stress 82.72 megapascal. 82.72 megapascal. Next, circumferential strain is given by, that is the equation. Sigma C is equal to, EC is equal to sigma C divided by Young's modulus minus Poisson ratio longitudinal stress divided by Young's modulus plus Poisson ratio pressure divided by Young's modulus equal to, we are taking outside of the 1 by E. So we can take it the Young's modulus. So 1 divided by E into sigma C minus Poisson ratio into sigma L plus Poisson ratio into PR, close the bracket. That is the formula we are using. So substituting the value of circumferential stress and longitudinal stress and pressure at the inner and outer surface. So we get the circumferential strain on inside surface. Circumferential strain on inside surface. Very, very important line. circumferential strain on inside surface. So inside surface, what are the circumferential values? Find out. So circumferential strains are inside surface. EC is equal to 1 divided by Young's modulus 210 into 10 power 3. Then we apply the 215.44 minus 0.26 into 82.72 plus 0.26 into 50. So we have simplified that values. We got the answer of circumferential strain 9.854 into 10 raised minus 4. 9.854 into 10 raised minus 4. So the strain have a no unit. Strain have a no unit. Next, circumferential strain on outer surface. Circumferential strain on outer surface. So previously we have calculated the inner surface, but we have calculated the circumferential strain on outer surface. So 1 divided by 210 into 10 raised 3, 165. We are changing the values. 165.44 minus 0.26 into 82.72 in plus 0.26 into 0. That is the outer pressure is 0. So we have a answer of circumferential strain on outer surface equal to 6.854 into 10 raised minus 4. That is the value of outer surface of circumferential strain. Next, longitudinal strain is given by so EL is equal to longitudinal stress divided by Young's modulus minus Poisson ratio into circumferential stress divided by Young's modulus plus Poisson ratio into pressure divided by Young's modulus is equal to 1 divided by E. Take it the outside of the bracket on Young's modulus 1 divided by E. Close the bracket. Sigma L minus Poisson ratio into sigma C plus Poisson ratio into PR. So longitudinal strain on inside on the surface. Longitudinal strain on inside surface. So EL is equal to 1 divided by 210 into 10 raised 3, 82.72 minus 0.26 into 215.44 plus 0.26 into 50. So we apply the values inside the formula. We got the answer of longitudinal strain in inside surface equal to 1.8907 into 10 raised minus 4. 1.8907 into 10 raised minus 4. Next we have find out the longitudinal strain on outer surface. So outer surface longitudinal strain is equal to 1 divided by 210 into 10 raised 3, 82.72 minus 0.26 into that value will be changed. That is 165.44 plus 0.26 into 0. So outer pressure is 0. So we apply 0.26 into 0. So the longitudinal strain on outer surface is equal to 1.8907 into 10 raised minus 4. That is the value of longitudinal strain on outer surface. The reference textbooks R.K. Bensal, Strength of Materials, Lakshmi Publications. Then another one of textbook is U.C. Jindal, Strength of Material, Asian Books Private Limited. Thank you.